Hello, in this video, I will discuss about the derivation of expenditure function and the Hessian demand function in case of Leontief preferences. Let us take a simple example of Leontief preferences is minimum x1, x2. Uh, so let us first solve the utility maximization problem and derive the indirect utility function. So in this case, we cannot use the Lagrangian optimization technique or our optimal condition MRS equals P1 over P2. So we use the fact that along the ray which passes through the corners of the L-shaped indifference curves, x1 equals to x2, and we substitute this in the budget constraint and we get the Marshall demand function of x1 as w over p1 plus p2 and demand function for x2 as w over p1 and p2. And the indirect utility function in this case is simply, this must be max, and the indirect utility function, we substitute this in the utility function bpw equals to mean w over p1 plus p2 w over p1 plus p2. So we substitute the value of x1 and x2, and since both the quantities are same, it becomes bpw equals to simply w over p1 plus p2 minimum of 1 comma 1, and which is 1. So in this case, the indirect utility function is simply w over p1 plus p2. So now let us go to the expenditure minimization program. The program is minimize p1 x1 plus p2 x2 by choosing x1 and x2 such that the utility is u bar. So here also we use the rule that along the ray the value of x1 and x2 are equal, so this becomes x1 equals to x2 equals u bar. So this gives us x1 is u bar and x2 is u bar, which are the compensated or the Hessian demand function for x1 and x2. So now we substitute this value of x1 and x2 in the expenditure function to get the expenditure function. So expenditure function denoted by EPU bar is simply P1, the value of x1 is u bar, plus P2 u bar. So u bar can be factored out. This becomes u bar P1 plus P2. So this expenditure function can also be derived from the indirect utility function that we derived a minute ago. So to derive the expenditure function from the indirect utility function, we simply substitute EPU bar instead of W and equate this to U bar. So we substitute EPU bar instead of W and we equate the value of function to U bar. And in our specific example, so instead of W we write EPU bar divided by P1 plus P2 and we equate this to U bar, and this simply becomes EPU bar equals to U bar times P1 or P1 plus P2. So this is the same as the expenditure function derived from the expenditure minimization program. So now we can see that this expenditure function has also the properties that we talked in an earlier video. Let us mention some of the properties. The first property is that this expenditure function is strictly increasing in U bar. So here the derivative is simply p1 plus p2, which is positive. It is increasing in price, so del E pu bar with respect to p1 or p2 simply equals u bar, which is also positive. So the expenditure function is increasing in price. The third property is that it is homogeneous of degree 1 in prices, homogeneous of degree 1 in prices. So here if we increase p1 and p2 by lambda, so this becomes u bar lambda p1 plus lambda p2, so which is lambda times the original expenditure EP u bar. So this is homogeneous of degree 1. And finally this expenditure function also follows the Seyfert's lemma. The Seyfert's lemma says that EP u bar is the derivative with respect to P1 is the Hickeyan demand function. So this gives us u bar, and this is simply the Hickeyan demand function x at 1 of pu bar. So we see that the Hickeyan demand is u bar, which is same as derived from the expenditure function. Similarly, we can partially differentiate the expenditure with respect to second commodity price, which is also u bar, and we see that the Hickeyan demand was x2 is u bar, which is same as we get from the expenditure function. So this is the Hickeyan demand function for the second commodity. So thank you for watching this video, and please keep connected to watch more videos in the future.